Hello and welcome to the video lecture series on contact mechanics in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at the Luleå University of Technology. And this is the fifth part of the first video lecture on contact mechanics fundamentals, and here we will look into the mathematical aspects of the system of equations at hand. So the outline of this presentation is like this. We will first make clear what are the inputs of the contact mechanics problems, and we will learn how to pose the problems by either specifying the rigid body movement or interference or the applied load. And in connection to this, we will go through what are the independent and dependent parameters of the problem, and in the end, two examples will be given. Some of the variables involved in the contact mechanics problems have already been described, like the gap, the deformed gap, and the pressure, the deformation, and so on. But let's now give this little bit more of devotion and try to define them very clearly. So what we see here is we have a lower surface and an upper surface. And assume now that these are completely separated and not in contact at all, then the undeformed gap G would just be the difference between the upper and the lower surface, or at least the shape of the gap G between the undeformed surface will be the upper surface minus the lower surface. And this is also what's of interest, since the actual datum will be given by the interference or clearance or rigid body separation delta. A dear child has many names, as they say. Other input parameters to the contact mechanics problem, at least for linear elastic surfaces or in linear elastic materials, are the Young's modulus and the Poisson ratio. I believe at this point it is perfectly clear that the pressure is a dependent variable and the pressure is a function of x and y, where x and y are independent variables, and we obtain P by solving the contact mechanics problem. Now, the deformation U depends on pressure and is therefore also a dependent variable. And if we take the interference as an input to the model, then the system of equations to be solved becomes precisely the complementarity problem that we see here below. So we have the deformation minus the gap between the deformed surfaces, undeformed surfaces, plus the rigid body movement or interference delta equals 0 whenever P is positive, and vice versa. There are, however, two different ways of posing this contact mechanics problem. And one is, as we speculated before, is to pose the interference delta as an input parameter. The other one, which is equivalent, is to specify the applied load as an input parameter. But if we do, then we would require an additional expression for the force equilibrium in the direction of the applied load. That is, sum of forces in the F direction should equal 0, and if we now denote the load, the applied load W, then W minus the integral of the pressure should be 0. And here the pressure, the X, could be in one or two dimensions. It's just a generalization of that, of Newton's first law in terms of the pressure. So these two ways of formulating the contact mechanics problems are equivalent, since we can either specify the interference as an input, and then we will have a contact pressure and the corresponding deformation, which leads to a deformed gap, will be the result. And the load W can be computed directly from the pressure just by integrating it over the domain. Then, if we take that applied load that we just computed, or we take the integral of the pressure that we just computed as the applied load, as an input, then we must find the interference delta, which would be then precisely the input specified in the first round, so that that force balance will be fulfilled. In this latter case, the interference is no longer an input parameter. It is now a dependent variable of the system, which must be augmented with the expression for the force balance, i.e. the Newton's first law. So we have a system comprised by the complementarity problem and a force balance condition. And then we solve this system of equations and we obtain the pressure and delta, which are the two main dependent variables of that system. The reason for me highlighting that the pressure and the interference are main dependent variables is that although the deformation depends on the pressure, it's only seen as an auxiliary dependent variable. However, this is also the case for the gap h between the deformed surfaces, as it's implicitly dependent on the pressure via the deformation u and explicitly dependent on the interference delta. Now, in terms of the gap between the undeformed surfaces, we can express the complementarity problem like this. So on the left hand side, we just summarize what we had before in terms of G, U and delta. And on the right hand side, we write this in a little bit different fashion and tell that H is always greater or equal to 0 and P is always greater than equal to 0, but the scalar product between H and P must always be 0. Just another way of formulating the complementarity problem. In summary, we have as independent variables x, which may be x1 and x2 if it's in 2D, and we have the dependent variables p, u, h, and maybe also delta. And it depends on the way we pose the problem. And then as input parameters, we have the gap between the undeformed surfaces, G, the Young's moduli of the two surfaces and Poisson ratio, and either the applied load or the interference between surfaces, dependent on how we formulate the problem. What Hertz did was that he was able to non-dimensionalize the problem and to find the universal analytical solution for it. And this is actually what we see in the window down here. We see the dimensionless Hertzian pressure profile, which is just a semi-cylinder with the radius 1. And we see also the deformed gap, which is obviously 0 in the region where the pressure is positive and positive elsewhere, so that it fulfills the complementarity problem, which this numerical solution also does for a rough HERTZIAN-like problem. Another analytical solution is the one by Vestergaard. Vestergaard, he studied a periodic surface roughness, namely a sinusoidally shaped surface topography with elastic properties, and this was pressed against a rigid plane. And he modeled the undeformed gap G by means of a cosinus function, and we had delta to model the amplitude and lambda to model the wavelength of this undeformed gap. Now he was able to obtain the contact width for each of the contact patches A, and he was also able to express this in terms of the pressure that fully flattens the surface when they are pressed against each other.